Hi everyone. In this section, we are going to learn 10 performance metrics in system design that we all should know about. And these performance metrics are very important. We're going to use them throughout the course. And these performance metrics will also affect the architecture of the solutions that we're going to design in our system design course. Now, today we will start with latency. So let's get started. Now, what is latency? Latency is basically the time taken by the signal to travel from source to destination. Now, in terms of system latency, we define it as a time taken by the request to travel throughout the system and then return back to client as a response. So let's understand this with the help of an example. So let's say we have a client and a server, and the client makes a request to the server, and the request takes time t1 to come to the server, and then server processes the request and then responds back to client in time t2. So the latency of the system is nothing but time t1 plus t2, which is also known as the end user latency. Now there is one more term that you will hear about, that is network latency. Now, what is network latency? Network latency is basically the time spent by the request and the response on the network. And as well as the time spent on waiting on the queues, if there are any. Now, let's see why calculation of the latencies are very important for a system. So latency affects the user experience of the system. Any user will always appreciate a system having low latency, okay? And it also affects the architecture of the system. So let's assume it affects the architecture. Now let's assume your system is having, okay, an SLA agreement with the clients, okay, and the latency of your system is more than the SLA that has been defined, the agreement that is there with the clients. So you'll have to change your architecture of the system so that your latency can come down. And to change the architecture, you might have to bring in load balancers, scale out your system, and then probably bring in caching, or probably introduce async processing in the systems. We'll cover all these topics later in the course, but for now let's stick to latency. Now, when we're talking about calculating the latency metrics, right, we broadly categorize ourselves in two sections, okay? One is average latency and the second one is tail latency, okay? Now tail latency. Now what do we mean by average latency? Now, average latency is nothing but a cumulative average of all the latencies for a given period of time, okay? So it's basically a cumulative average of all latencies in a given period of time. So let's understand this with the help of an example. Let's say in the last 1 hour, I want to calculate the average latency of a system. And in the last 1 hour, let's say we assume that we have request R1, R2, R3, R4, R5. There are 5 requests that has come, and the corresponding latency is L1, L2, L3, L4, L5. So we just sum all the latencies for all the requests in that given period of time divided by the number of requests. This gives us the average latency of the system. So let's say there are n requests. So this becomes my average latency for a time period. Now, where are average latencies used? So average latencies are used where in a system which are not time critical, or let's say when we are comparing two algorithms or two systems, which is better, which is not better. So let's for example, let's say log aggregation systems or batch processing, or let's say in data processing in Hadoop servers will generally go with average latencies. Now coming to tail latency. What is tail latency? Tail latency. Now, tail latency refers to the shortest request response in a system, basically highlighting the outliers of the system. So let's take this example only. Let's say we have 5 requests, that is R1, R2, R3, R4 and R5, and the and the latency is 2, 4, 7, 10, 3. So these two biggest latencies, that is 7 and 10, that is request R3 and R4, would be the one determining the tail latencies. Okay, because these are the outliers of the system. Now you would also hear about term latency percentile, tail latency percentile. So what are those? Let's say we have P50, P90, P95, which is equal to, let's say, 10 milliseconds. Okay, so what does these terminologies mean? So these numerical values tell you that 90% of the request, let's say if we talk about P90, 90% of the request would be completed within this tail latency barrier, that is 10 milliseconds. Okay, and if we talk about P50, that is we also call this median latency. So it's around 50% of the request will be completed within the within this tail latency barrier of P50. Okay, and where are these tail latencies used? These tail latencies would be used in systems which are very time critical. Okay, for example, in financial institutions, or let's say in trading, because the tail latencies are basically the most observed by the user. Why are they most observed by the user? So let's say if there are 10 requests and the average latency of the system is, let's say, 5 milliseconds. Okay, so the 10 requests, let's say, are getting completed in 5 milliseconds. So the user is expecting his 11th request as well to be completed in 5 milliseconds. But let's say if in some scenarios the 11th request takes 10 milliseconds. Okay, these are the outlier requests, right? So the user observes that request, that because he was expecting 5 milliseconds for that request, he was expecting it to be completed in 5 milliseconds. He saw that that request completed in 10 milliseconds, so he will observe that this particular request took more than expected time. So that's why we say that the outlier requests are more observed by the user. Now coming to tail latency, we also have one point wherein we have tail latency amplifications. Now what is tail latency amplification? So let's assume a request is traveling through multiple microservices in a distributed architecture. So the probability of that request hitting tail latency in one or more services increases as more and more microservices are added in the distributed system. So let's take an example. Let's say we have one microservice and the tail latency of that service is, let's say, P95 is, let's say, 10 milliseconds. Okay, and there's only one microservice in the system, in the whole of system. Okay, so the request comes and we get a response. So the probability of this request hitting having a latency of more than 10 milliseconds is going to be 5%, right? Because 95% of the request is going to have latency less than 10 milliseconds. So the probability of this particular request having latency more than 10 milliseconds is 5%. Now let's take an example that this request goes into a system, and this particular system is having 10 different microservices, 10 microservices, 1, 2, 3, and similarly till 10, and it travels throughout those 10 microservices and we get a response, right? So the probability of, so we will calculate the probability of this request hitting one or more tail latencies, one or more microservices with tail latency. So let's say what is the probability of this request hitting all the tail latencies in all the microservices? So we have 0.05 is here. So and then we have 0.05, then we have 0.05, then we have 0.05. Okay, and similarly if we calculate the tail latency, like if we calculate the probability of this particular request not hitting any of the tail latency in the system, so it is going to be 0.95, 0.95, 0.95, assuming that the P95 of all the microservices are equal, 0.95. So what is the probability of this request of not hitting any of the tail latencies for any of the microservices? 0.95 to the power 10, 0.95 into 0.95 into 0.95. Okay, so the probability of this request hitting at least one is 1 minus 0.95 to the power 10, which is approximately equal to 40%. Okay, so from 5%, the probability of this particular request having a tail latency of more than 10 seconds was 5%. And here the probability of this request hitting any of the tail latency for this microsystem changed to 40%. So this is your basically the tail latency amplification. So that's it for today. We'll see you tomorrow again. Thank you.